J-Sol is a Japanese IT consulting services corporation. It was founded in 2006 and provides a variety of solutions from software development to technical support and consulting in CAE field, so in computational aided engineering field. There you have the link to their webpage in English version. So as I mentioned before, J-OCTA is one of the products of J-Sol. Since 2017, Simone and J-Sol established a partnership for product co-development. This included the development of interface tool as well as Siesta Modeler in J-OCTA. So these two modelers, these two tools, are now part of the J-OCTA platform. Since 2024, Simone became official distributor of J-OCTA in most of Europe and in US. At the same time, also J-Sol became distributor of ASAP, Simone software in Japan. So going more into detail of talking a bit more about J-OCTA. So J-OCTA is very important to say that it's a multi-scale simulation software that can predict properties then in a very wide range of scales from the atomistic to the micrometer scale. And it can do so for a wide range of material such as resins, rubbers, nanocomposites, batteries, but not only, also in life science fields such as drug discovery and pharmaceutical formulation. Now, what you see here on the left is the image of like the starting page of the J-OCTA software, but we will look at it in detail in the second part of this webinar. Now, it's important to say that J-OCTA is the commercial version of OCTA. OCTA is a national project, an open source initiative started in 2002 in Japan. And since 2005, J-OCTA was developed by J-Sol, and J-OCTA is the commercial version of OCTA. And it has a very complete graphical user interface and is directed to industrial users. And I'm going back to the concept of multi-scale because I think it's very important and fundamental. Here you see on top the scales, the range of scales at which J-OCTA can simulate. So at the bottom left, you have the small scale. So we are talking about nanometer scales with modeler and engines such as Siesta and Gaussian that use density function theory and molecular orbital method to get electronic properties. And then if we go up one step, we find modelers such as Cognac, VSOP, which are included in the J-OCTA platform, and third-party code engines such as LAMPS that are supported by J-OCTA. That works with methodologies such as atomistic and coarse-grained molecular dynamics. If we move up again, we find Pasta, Naples, VSOP, DPD, specialized in tube model, Sushi, working with mean field method, Muffin, finite element method, and finally VSOP-PS with MPS and SPM. Now, one thing that is very important to mention here is that this scale is not static, it's mobile, meaning that J-OCTA provides all the tools to move in this scale. So you can start a project on one scale and end up in another. This is very important because often you might need to set up the system starting at a very small scale, and then you need to increase the size of the system in order to tackle and to calculate certain properties that can only be described as a mesoscale, in a mesoscale range. We can go up to these stairs as well as we can go down. I will show you after in the demo with what is called reverse mapping. So this means that you can create a model using, for example, as I will show later, a coarse-grained method, and then decide to go down in scale and go back to a full atomistic description. This is, I think, is a very powerful, innovative feature of J-OCTA, that you don't need several tools to perform multi-scale simulations. I mentioned now about the spatial scale, but the time scale is as important as the spatial scale. For example, if we think about rubber materials. On the right, you see like the spatial scale, where you see like the tire that can be seen as a polymer made of atoms. And then you can go up in scale and consider aggregates as a basic unit or agglomerates. But at the same time, also the time scale is very important. For example, if we are looking at the stress response of material, strain stress response with time, we see that depending on the properties that you want to characterize of a material, you might need to use different kind of models. So full atomistic or coarse grain or tube models or more. In this case, for the rubber materials in general, there are 3 different regions: the glassy region, the rubbery plateau, and then the viscous region. And each of them needs to be tackled with a proper modeler, with a proper engine, with a proper methodology, because they span time range very different. Now, always having in mind polymers as material, this multi-scale approach is fundamental, and we can range from nanometer to micrometer scale. Here you see summary of what you can do at each scale. So in the small scale, we have methodologies such as quantum chemistry and DFT, density functional theory, which helps you to get information about energy band structure, molecular interaction, in general electronic properties, and J potentials. I mentioned this because I think it's quite important, because Lennard-Jones potential can now be used in the next model, which is full atomistic molecular dynamics. Again, you see the connection between the models working at different scales. Full atomistic molecular dynamics is very good for evaluating polymer density, elastic modulus, volume distribution, gas diffusions, and many more. Next scale is a coarse grain molecular dynamics. In a few slides, we will see what this means. Useful for self-assembly analysis, polymer morphology. DPD, dissipative particle dynamics, mentioned before, a mean field method, useful for shaping polymer chains and study phase separation, as well as dispersion of fillers in the structure. Reptation dynamics, to get information about viscosity, relaxation time, stress strain response, and in polymer melts. So you see we are increasing the size of the system, as well as the time span from by the simulation. And then you have a continuum model to get average elastic modulus and thermal conductivity, so mesoscale properties.